Okay, so today, typically we would be at lesson 2.6, and we would just be covering really two parent functions. So what I'm doing is combining several different lessons. We're just going to go ahead and show you all of the parent functions that you're going to be responsible for knowing. And instead of doing like the book and break them up into sections later on in the semester, we're just going to do them all today. So every parent function that you're going to need to know, you're going to be exposed to today. And then we're going to be doing what is known as transformations. And there are three. So that's why you have three of this sheet. Okay. So what I want you to do right now is take these sheets before we get to Desmos. And at the top of one of them, you're going to write the word translations. All right. So grab one of these sheets and write the word translations at the top of one. And then at the top of another one, you're going to write reflections. Reflections. And then at the top of the third one, you're going to write dilations. Dilations. D-I-lations. Together, those three different effects on graphs are called transformations. Okay? And our lesson today is really twofold. I want you to know what the parents look like, and then I want you to know what the graphs of the parents look like after we've performed various transformations on those graphs. Okay, so that's the goal for today. So I thought we would look at Desmos just by way of introduction and let you play around with it a little bit. Let's just start with one of our parents that we're already familiar with. So first of all, with Desmos, you probably want to show the keyboard. So you see how you can do that. And this is our formula bar. So we're going to make a function y equals, and let's just do, let's put y equals x squared here. So you have x. So, well, right there is one of our parents. There's y equals x. So let's make this y equals x squared by hitting the a squared button so everybody has that picture. All right. So that's one of our parents. Now we can do what is known as a translation of this parent. So let's do this. We're going to use our parentheses. And inside the parentheses, we're going to do x, well, let's say plus 3. And then we're going to put the parenthesis to the second power. What's the effect of doing that? Where did our vertex go? So we've already talked about that. Just to review, this is tricky, but the actual vertex form, can't get too far away, looks like this. If you wanted the technical algebraic vertex form, which is what this is called, the reason why, if you're wanting to know, why is it opposite? Why is the horizontal shift always the opposite of the way you think it should be? And the reason for that is because of this H. H stands for the horizontal shift. Okay, so you need to watch this because what I'm saying right now is more important than what you're doing. Okay, everybody with me? Okay, so how did I move, left or right? Okay, that means the H number, if it's left, should be what sign? Shouldn't it be negative if you're moving to the left? So what happens if you put -3 in for H in this form? What's it become? So that's the reason why if we start with this and we input a negative number, which indicates shifting to the left, it forces our original to become plus. So that's the reason behind the horizontal shifting always being the opposite of the way we would think it should be. Okay, so go up there in your formula bar and make that become -5 instead of +3. Just change it to -5. We're just playing around. I think the more you play with this and the more you see it, the easier it is to remember these translation rules. So everybody do it. All right, what's the effect? So you did -5, it went to the right. Okay, now let's include a vertical move. So inside, now this is going to be true for all the parents, so I hope you're listening. Anytime we do an operation plus or minus inside, whether that's parentheses, whether that's absolute value, whether that's the square root, that's the cube root, it really doesn't matter. Anytime something is performed on the inside, that's always indicating a horizontal shift. Okay, and the horizontal shift is always the opposite of the way you would think, and it's because of this. All right, so now let's include a vertical shift. That's when we go outside. So let's do a plus, and just take, it doesn't really matter what your function is on the inside, and let's just do +3. So the shift that's indicated on the outside, the operation, is always a vertical move. And as you can see, the vertical move isn't tricky. It's nice. Plus is up, minus is down, just like all is good in the world, nothing tricky, but you do have to be careful with the inside, the horizontal shift. All right, so that's called a translation. That's one of our transformations. And while we're here, let's just go ahead and touch on another transformation, and that is when I put a negative in front of the parentheses. Do you see what happened? And that's true for all parents. So the great thing about these transformation rules is once you understand them, they apply exactly the same to all parents. So that flips the cube root parent. That flips the absolute value parent. If I put a negative in front, it just takes that parent graph, the translated parent in this case, and it flips it over. It's called a vertical reflection. All right, and then we're going to look at some other parents in just a minute. Let's do this. I'm going to put in front of the parentheses, I'm going to put multiply by 2. So I want you to look, if you didn't catch it, take the 2 off and then put it back. What did it do to the graph? How would you describe it? Somebody say something. I can't hear you as well, so you have to speak up. The slope, okay, I mean, technically parabolas don't have slope, but I think I understand what you're saying. Yeah. Steeper, it may got another adjective. Thinner, maybe skinnier. Okay, everybody agree with that? All right, let's do it even bigger. What if I put 6? So you kind of made the conjecture that the bigger the number, the skinnier the parabola, right? Well, this is another transformation. This is a dilation. Dilation means that we're still going to have a parabola, but it's going to be a different size. And the size is either going to be skinny or fat. We actually have words for those. What happens when I multiply by a whole number is it accomplishes what's called vertical stretch. And that's just another way of saying it takes the original parent and it literally, if it were elastic and you pull up on it, it's going to kind of make it go more and more narrow. Well, the flip side of vertical stretch, let's do a fraction. We'll just do like 1 divided by 3 in the front. What's the effect? Yeah, so you'll hear some math teachers in the future say vertical stretch and vertical squish. It's kind of like if I applied pressure from the top on a static object, it's going to just make it go wider and wider and wider until it's all being pushed basically against the x-axis. So these are called dilations. So we just looked at all three transformations with one of the parents. Translation is a shift. Reflection is when we put minus in front. It's going to be a vertical flip. And then dilation is when we either multiply by a whole number. What's that called? A whole number? Vertical stretch. Good job. And when I multiply by a fraction, vertical squish. The technical word is compression. So if you have a math teacher that likes to use literal math words, they might say vertical compression. But I know a lot of teachers like stretch and squish. Okay, skinny, fat. Okay, so that is all performed on one parent, and that's the quadratic parent. All right, now I want you, just playing around with this, I want you to take this parent. So let's hit the absolute value, put x in the middle, and I want you to perform all of the different transformations on that one parent. So you should be able to show translation, both horizontal and vertical, vertical reflection, and I want you to do stretch and squish. Okay? Try it. Put all of those transformations in one function. And if somebody would care to volunteer and read me your final function that involves all of those transformations. You've got reflection, you've got a horizontal shift, you've got a vertical shift, and you've got, well, let's start with stretch. Somebody want to give me their function that involves all of those? Allie. So describe for me all of your transformations. Good. Vertical reflection, very good. Yeah, so you just heard kind of like a test question. Write a function for this parent that is reflected vertically, shifted 5 to the left, 2 up, and it is stretched by a factor of 5. So you should be able to do that. Anybody have a question? How we incorporate all of those transformations in what we call parent functions. All right, so we're already pretty familiar with the parent u, x squared, and the parent v. So let's take a look before we get to our actual written part of this. Let's take a look at some parents that we're not as familiar with. And we're going to do the square root of x. The square root parent. What do you notice about this parent? Anything? Allie? Say it one more time. It has a starting point, and then it only goes in one direction, left or right. Yeah, so in behavior language, you would say as x approaches positive infinity, y approaches positive infinity, and it doesn't go to the left at all. Why is that? Anybody know? Exactly. Man, he's on fire over there. What if we put -4 in for x here? Your calculator is going to say, I can't do that. Yeah, not on this graph paper. And all we're concerned about on this graph paper are real numbers. Now, there is a graph paper that involves the complex numbers, and we're just about there. Next week, we'll be there. But right now, we're just interested in graphing real numbers. So I want you to take this parent and I want you to translate it both vertically and horizontally. You can do whatever you want, and then I'll ask somebody what you did. So for now, we're just going to do the horizontal and vertical translations on this parent. Just type it in, and then you're going to do, on this parent, you're going to do both a horizontal and a vertical translation. And I'm going to get somebody besides Allie. Allie went first. So, Landon, what do you have? Very good. +1. Okay, so underneath the radical means he went right 1. Remember, it's the horizontal shift is always opposite of the way it looks. And then outside the radical is the vertical shift. Somebody have something else different? Yeah. Okay, very good. Now, what would be necessary, Trinity, to reflect this vertically? Boom. All right, let's reflect it. Negative in front of the square root. And now I want to perform vertical compression. So somebody give me a way to perform on this. We're going to include vertical compression or vertical squish. So you got it? Yeah. Okay. Yeah, that's going to be big time. 1/10. Yeah, it's almost linear. I mean, it's not, but it really squishes it from the original. Now, let's change it from vertical squish to vertical stretch. Somebody else. Caroline. Now, don't misunderstand. The negative technically isn't the stretch, but what is? Yeah, what is the negative? That's the reflection. Okay, I just want you to I want to make sure you're clear. Now the 5 is the stretch, and it's because it's negative, it's stretching downward. Okay, everybody good with the square root parent? All right, let's do another parent. Cube root. Unless somebody finds it, I don't see an automatic cube root, so I'm going to do cube roots like this. I'm going to raise x to the 1/3 power. Oh, not like that. So this a raised to the b, and the exponent, you can just do 1 divided by 3. Raising something to the 1/3 power is the same thing as the cube root of. So there's some similarities, but there's an obvious difference between this and the square root parent. What do you see? Where the square root parent, Allie told us, had an endpoint and it just went positive. It's like a curved ray. This one obviously does what? Why is that? Why does it go both directions? Is there a way to do the cube root of a negative number? Like, what's the cube root of -8? -2, right? So isn't that on our graph? Here's -8 input, here's -2. So it is possible. Unlike square roots, we can't do the square root of negative number in the real number system, but we can do cube roots. All right, reflect it. Reflect it. Vertically, I should say. There is a horizontal reflection, but we're not interested in that. Harper, what'd you do? All right, good. Flipped. Okay, let's see, Joel, I want you to translate this 3 units to the left. What will accomplish that? +3. All right, do you see how that's called that inflection point now is the one in the very middle where it changes, kind of changes direction. That's called a point of inflection. And now, Allison, let's move it 2 down. There we go. Easy peasy. Any questions? I guess your job is just to remember. I'm going to give you some, when we get to the paper, I'm going to give you some ways that you can always, if you forget what the shape is of the parent, you can just do a little bit of mental math and come up with them. All right, let's see, that's several of the parents. We need to do x to the third. So I'm going to do x raised to the third power. I think we looked at this the other day. So Trayson, I want you to perform vertical compression on this. You said 5? Well, that would be vertical stretch. All right. Let's see what that does. What's that effect? Yeah, so it takes it, the original parent makes it a little bit wider. We'll keep with that. Let me see if I not caught on. Alex, can you translate this 4 units to the left? I'm sorry, Jones. So I'm going to have to change this a little bit because if I just do this, I just want to make sure I'm clear with what you're saying. If I just do this, what's the effect? Yeah, so to show horizontal, I've got to enclose it. So what's that going to look like? All right. Yeah, we'll have to do a little adjustment here. All right, so what goes in the parentheses again? If I'm going x plus 4, good. And now we'll need to raise this. And a lot of people fail to do what I'm doing. They like to put the exponent in here with x. But what if I did? What if I just left the exponent here? What am I doing? Like if it just said 1/5 quantity x cubed plus 4, if I had the exponent and I took it and put it right there, essentially what have I done? I've done a move, but which move? I've moved it vertically. I don't really need the parentheses in this case. If you add or subtract directly to the without the parentheses, then you've done a vertical shift. So the bottom line here is make sure if you're doing the horizontal or the vertical shift, you put the exponent on the outside of the parentheses. That's a pretty common mistake that people make. And then what was our other move? I've already forgotten. Or did I just say left? Okay. Let's see, Abram, I want to go 3 up. And I want to reflect it. Olivia. There we go. Good job. Let's see. I think we've gotten all of our parents except for one. We got one more to go, and this is called the reciprocal function parent. And we need to make a fraction. And we're going to put x in the denominator. All right, so anything that is being directly added or subtracted to x. Now, typically that's going to be either inside parentheses, absolute value, or it's going to be under a radical. But here it's just going to be literally added to or subtracted from x. So let's see what happens. When I add or subtract directly to x, that creates the horizontal shift. So in this case, I went 4 to the right. And then when I go off to the side and I do another addition or subtraction, that creates the vertical shift. And the way I accomplish the dilation is I just increase this. I'll make this 6. And the way I perform the reflection is just like before. I just put a negative in front and it flips the whole graph over. Okay, so I think we've played around with this enough. Let's go to your sheets, and we're actually going to write some stuff down that will be what you would call your notes. Anybody have a question? All right, so let's go to the one that you've labeled translations. And if you have colors here and you want to differentiate different graphs, we're going to be doing probably 2 or 3 graphs on one graph section. So if you do them in colors, it might help you keep them straight. Or you could just label the graphs if you're not doing colors. So you can put your device away. And let's run through all of the parents one more time. This is going to be helpful if you're not really sure how to make the parents. They're not just random. They have actual points that we use to plot, but I'm going to show you how to come up with those points. Well, y equals x is pretty easy. That's just a line that goes through the origin. Hopefully yours will go through the origin, not like mine. It has a y-intercept of 0 and it has a slope of positive 1. So since this is our translations page, let's do some example translations. These are pretty basic. If I take the parent, y equals x, and I add 2, there really technically isn't a horizontal shift here. I just always think of taking the parent and it's just a vertical move. We're going 2 places up. So every point on the parent is going to go up. You just start, all of these start with the parent, and then you just take all the points and you move them according to the shift. So that would be y equals x plus 2. I'll let you connect them. I'm not going to try to take the time to do that. And I can't change colors real quickly, but if you have color, feel free to use it. And we'll do one more. So y equals x minus 5 starts with the parent. If you think about it, every graph of a function is just taking the parent and transforming it into a child graph. So this is y equals x shifted 5 units down. All right. Now y equals absolute value of x, the absolute value parent v, vertex at the origin. Slope of positive and negative 1. Yeah, Olivia? Are you talking about this? It's hitting the origin. I just missed it. So it's like you start at the origin and you just count a slope of positive 1. So all of these are going to have the origin in common. Every one of these parents will, well, I should say except for our last one. Well, it's a little bit odd. Okay, so the absolute value parent looks like this. And when we translate the parent, we looked at that. Here's an example. What's my translation here? Right one, up 3. So again, it's going to get kind of messy, but if you want to color code these, or at least just label them. So there's the translated parent. Y equals x squared. Remember, some of you graphed this as a linear, but if you think about how the word squared is spelled, that might help you remember parabolas are always produced from this function. Now, don't give me just a random u, just do some simple inputs. Obviously the origin, but what if I input 1 for x? What comes out? 1 squared is 1. What if I input -1? What if I input 2? 4 and -2. So when you're looking for guidance on how to draw these parents, you can always use just simple inputs, 0, 1, and 2, and that should help you get a basic drawing. All right, there's the parent. And let's do a translated parent. So Harper, how did I translate the parent here? When you say +2, right 2, right? And then up 1. Very good. And that becomes your new graph. So every one of these points, they just move the same way. Every one of those 5 points go 2 to the right and 1 up. And then you make your new U from there. It's going to be easier for you to do on paper than it is for me on this, but did I lose anybody? Scroll down. Oh, slow down. Okay. Any questions? All right, let's get the, is that okay? Let's get the parent graph of x to the third. Just use the inputs 0, 1, and -1. So if I input 0, what comes out? What's 0 cubed? All right, so goes to the origin. What if I input 1? 1 cubed? What if I input -1? All right, so you kind of get the idea. What if I input 2? 2 cubed is 8. -2. So it's kind of like a skinny version of an S, I guess. Man, my eye-hand coordination is going fast. All right, let's translate it. Caroline, left 2, up 5. Very good. So you just take all of those points that we just plotted and do the same for all of them. Left 2, up 5. So this would be the translated parent. And I'm just doing one sample, but hopefully this makes sense. You guys are doing great. I think we can save some time by just putting all this together as one lesson. Okay, the square root parent. We talked earlier when we were looking at Desmos, we can't input negative numbers. The square root of -4 is not real. So we start at 0. What's the square root of 0? And then for inputs, if you want to know what this actually is in terms of points you can connect, let's just put in perfect square root numbers for x, starting with 1. What's the square root of 1? Input 1, output 1. What if I input 4? Input 4, output 2, and then what's the next perfect square number? And then that gives me output 3. And so we'll just use those as our reference points. And that's what the parent looks like. And we'll do another translation. Let's see, Allison, what's this represented? What kind of translation? Left 4, down 2, and all of the points on the parent follow suit. You just take each one of them and move them those 2 directions. Question so far? Now the cube root still goes to the origin, but now we're going to choose perfect cube root numbers. Well, 1's a good one. What's the cube root of 1? And the cube root of -1. After 1, what's the next perfect cube root number? 8. So input 8. And what's the output? Cube root of 8. 2. 2 times 2 times 2. And we can also do the cube root of -8. That's why this goes in both directions. So it's kind of like this guy, x to the third, kind of, but it's turned on its side. And then I think you get the translations, how to move left, right, up, and down, so I'll try to save some time. Now, the oddball of the group, because what is one number that we cannot let x be in 16? It's impossible to divide by 0, so 0 can't be an input. This one graph out of all of our parents does not go through the origin. So let's pick some other numbers that we can use and make the math easy, like 1. If I input 1, what's the y? If I input 2, what's the y? What if I input 1/2? Dividing by half is the same thing as, so if I input 1/2, I get 2 as the output. So what happens here is we have a graph that's really in 2 different parts. And we're going to deal with this term more later, but I'll go ahead and introduce it now. We will approach the x-axis forever, but we'll never get there. Interesting. There's no way to ever get x equals 0 out of this, and there's no way to ever get y equals 0. We can't input a number in for x. We have what we are called asymptotes. Just file that away for later. An asymptote line is a line that a graph will always approach. It'll approach forever and ever and ever. It'll just get closer and closer and closer, but it'll never actually touch. So going toward positive infinity, if I input 1 million for x, I am way, way over there to the right input, and I'm off the x-axis by 1/1,000,000th, but I'm not at 0. I'm not actually on the x-axis. And that same thing is going to be true for y. There's no number I could input for x to make y equal 0, so I'm going to approach both of these forever. And because we can do the opposites, we have what are called 2 branches. So this graph is always going to be graphed in 2 parts. And if it's not reflected, they'll always be in quadrants 1 and 3. Okay, do you have questions for me? Any questions? Yeah. Anybody else Do you think you know what the parents look like? I heard two things. Say it one more time. What we just did are translations. So I might save a little bit of time. What I was planning to do is the same parents on the dilation sheet, they all just get flipped. But I just want you to make sure you understand what the parents look like, how to make them. All right. Let's go to the dilation sheet. I think we could save a little bit of time and we'll just talk about dilations real quick. And I'm going to summarize this for you. Yeah, it's going to be on the test. Can you do it? Yeah. In front. Hmm. Yeah, we're not going to worry about horizontal flip. I'm just going to keep it. No, we're not going to. I'm going to save some time. A horizontal flip would be you put the minus on the inside, but it would just take the V and do this, and it goes back to its original position. So I'm not worried about those. I want the ones that actually make a change in the graph. So all of these are going to be all of the ones that you're going to be doing for me will be vertical reflections. So I think we got that pretty well. Let's talk about dilation. So go to your dilation page, and I don't think we have to do all these graphs again, but let me just kind of summarize dilations for you. And again, I'm only going to worry about the two vertical. There are two horizontal dilations as well, but I think I'll cut to the chase and just deal with what's more common. For all the parents, I'll just take, for example, well, let's take the quadratic parent. We'll do it like this. If I put a number here in place of A, that's greater than 1, we have vertical stretch. Now we saw many examples of that on Desmos. If you want to take Desmos, it's a great thing to do. Just play with it. Put in your own functions, change the numbers around, see what happens. We did a little bit of that. I wish we had time to do more of it. It's a good way to get familiar with how these work. So stretch is skinny. All right. So the bigger the number that we put in front, that would also be true for all parents. So I'm not going to belabor the point, but here's the same thing. I'm taking this time it's the square root parent, and I'm causing vertical stretch if the A number is greater than 1. All right. If the A number is a fraction, or it could be a decimal, between 0 and 1, then we have, the technical term is called vertical compression, but you can think of vertical squish. So I'll use a different parent. And that applies to all parents. All right, you guys done really well with this. Is there a question I can answer? We're going to do some practicing with these on these pages. And then how do you feel about tomorrow? Did you have any questions about tomorrow, what to expect? Have you done your own practice, test prep? I probably want to do that. You got a little bit more pressure because tomorrow's Wednesday. You don't have quite as much time, so you're going to have to really know your stuff. You shouldn't be debating with yourself on what to do. You should just come in and know it. Caroline, that's a good question. Yeah, It's this, yeah, this is something I've never done before, so it's going to have to be changed from last year. So I don't really know for sure, but I will take it and I'll see, I'll make sure it's doable in 65 minutes. I think you have 65 minutes. Yeah, don't labor too long on one problem. Yeah. You should have gotten test objectives. So, did you read them? Okay. That'll answer your question. Yes. Well, I might give you a graph of a parent and tell you, give me the equation. Or what these are, you're going to be taking the equation and get the graph. So it could be either one. I'm not going to do 16 tomorrow. You don't have to worry about that one, but you should be good with all those others. Yeah, any of those others. They're Do you not know how to do 13? So just think input 0, 1, and -1, and that'll help. Yeah, you're going to get used to these, and this is you're going to have to face forward. We've already been through this. It's, um, all right, I lost my train of thought. What was I saying? Yeah, pre-cal. You're going to need to know these really, really well. This called family of parent functions. So you're going to get a lot of exposure to them. I want to prepare you for pre-cal. All right, those are in your textbook, and we'll see how much we can get done. I really don't want you to have to do anything assignment-wise tonight because I want to free you up for test prep. So let's see if we can. You have graph paper for doing these. There's really not that many because you're only doing evens and odds. So I want to see if you can sketch those graphs, and if there's something I can do to help you, let me know.